Looks great.
Okay, let me make a short introduction. I'm pleased to have Sarah Nickerson here. She's one of us. If you scratch deeply enough, not too long ago, she was an undergrad in our physics and astronomy program. After that, she went to the master and worked on the missing satellite problem with Hugh Coachman, and then got lured to the University of Zurich. It's very adventurous.
Yeah.
And continued working on simulations. Then, even more adventurous, she applied and was selected to work at NASA Ames through this Bay Area Environmental Research Institute, where she is now. And she also bravely pivoted to work on something of interest to a lot of us, which is massive stars. And she's going to tell us about what you can learn, especially from the mid-infrared. She's been connected to that stratospheric observatory that flies planes, Sophia, and now retired, but Sarah's not retired, and she's going to be able to tell us about these massive star forming regions. Perhaps you could turn one of these lights off and you'll there, that's good. Okay, take it away.
All right, thanks for the introduction. As I shall reveal, there's still, even though Sophia no more, it's sitting in a museum in Arizona, there's still a lot of data. There's always too much data and not enough astronomers. So I'll begin by showing you a pretty picture, because this is what we think of, what we go into astronomy for, are the beautiful images. So this is a low-mass protostar taken with JST NIRCam, and you can see a lot of features already. So the protostar itself is hidden at its early stages. They're deeply embedded in the dust and the gas from which they were born, and so we can't see them directly, but we can see their effects that they have on the environment around them. And so the protostar is buried here, deep in the center, and you can see there's a dark line in the middle, and so this is an edge-on disk, an accretion disk around the protostar that's feeding it. And the hourglass shape, you have the cavities that's been carved out by two massive outflows, and you can see the effects of dust extinction, where here there's less dust, so more blue light can escape, but here it's reddened, there's deeper dust, and there's also, you can see the clumps of shocked H2 gas. But there's more information that can be gained when you go to spectroscopy, which at first it looks less beautiful, messier. So this is some data from the mid-infrared towards the entire region. And here's a long and then zooming in, you can see there's different ion features, H2 emission lines, and what I'm talking about, what I specialize in, is the molecular lines. So we have a model of water transitions, and so I hope for those of you who haven't done spectroscopy, by the end of my talk, you can appreciate it a bit more. So just going back to some of the basics, there's three kinds of spectra. There's continuous that's emitted from a source, normally a star, and then you have hot gas that can make emission lines that happen at certain discrete wavelengths. And then there's absorption lines, which you have some colder gas in front of a source, and then it will selectively absorb the continuous spectra from it. And emission lines happen when the electrons move to a lower energy level, they emit a photon. Absorption lines happen when it absorbs a photon and moves to a higher energy level. And from quantum mechanics, these happen at discrete energies. And so for molecules, they can have all kinds of different transitions. They can stretch, they can bend, they can twist. And each type of transition yields a unique pattern for that molecule. And that's how we can know which molecule that we're looking at by its signature patterns, its fingerprints. And then we can also gain other information by how much its spectra shifted. So this way we can get the velocities in the Z direction. And these molecules are everywhere in the universe thanks to stars. And so stars are the source of enriching the universe since the Big Bang. And so you have the gas that forms the stars. They create the two different types of stars, the low mass stars and the massive stars. They go through their life cycle, and then with their deaths, they enrich the universe again, thus increasingly enriching everything. The high mass and low mass stars go through different processes of creation. How different they are is still a very active field of research, and a lot of debate going into it. Some main differences, you have the low mass stars. Well, they both start out as in the cold molecular clouds, the gas collapses, and then you have the hot molecular core or hot carino part, which is rich in molecules. I'll talk on this later, because this is the stage of star formation that I'm interested in. The high mass stars, they go on to ionize their environments, they blast away all those molecules, whereas the low mass stars, they'll form protoplanetary disks, and they'll gather that molecular material and eventually form planetary systems like the one we live on. And these hot molecular cores, these are warm, small, dense regions of gas that are associated with high mass protostars. Typically, they're surrounding the protostar in an envelope, but there's also irregular ones that are, say, if the star has a H2 region, the ionized H2, not the liquid H2, an ionized region around it, it might compress the gas outside of it to make a hot core, but typically they're around the star. And why these are very interesting for spectroscopy is that in the previous stages in the cold molecular clouds, molecules either freeze onto the dust grains or they're also formed on the dust grains as a catalyst. And so as the protostars turn on, as they heat up their surroundings, they will release these molecules into the gas phase. And then there's further molecules formed through gas phase reactions. And so this is a good probe both of the past, of the clouds, the cold clouds that formed the stars, but also looking into the future, what kind of new molecules were formed in the gas phases. And so these are very rich targets for spectrographs. And they were first discovered around the massive stars, but low mass protostars also have corresponding hot carinos around them. And so they're very interesting because we're also looking, I think actually I covered this slide on my previous slide. But just looking at the bigger picture, it's interesting that we want to trace back the molecules that give the origins of life. We want to know what's their availability, what stage are they made at, how did they made, how did they get there, what conditions are they made in. So we want to be able to constrain life by constraining the availability of the molecules of life. And hot cores, even though they themselves are not going to form planetary systems, they're the very strong probes of the type of gas and the type of regions where stars like our sun were formed. It's thought that our sun formed in a high mass star forming region. And so by looking at this, we can think of maybe where these molecules came from and decide how much was inherited from the cold, icy dark phase and how much is manufactured in later stages of star formation. And so why the mid-infrared? What's interesting about mid-infrared? And so mid-infrared around protoplanetary disks, it's capturing the warm inner regions. And this is where, around systems like our own Earth, this is where we see the rocky planets. And so there's different theories about, did the rocky planets form in situ? Did they migrate in? But either way, this is the region that has a huge influence on the molecules. that will form places like Earth. And around the high mass protostars, this also probes the inner regions. Commonly, molecular surveys tend to be at longer wavelengths, at radio wavelengths, because this is very accessible from the ground. And these probe the outer regions of the disks, outer regions, the colder outer regions. And so by going to mid-infrared and also near-infrared, we're really probing the hot gas at the heart of these systems. And all these different wavelengths we can access in different ways. Of course, optical, you get a lot of that from the ground. It's no coincidence our eyes see. This is the wavelengths we're most familiar with. You go shorter, you have to go to space, and then you go longer with infrared. There's also a lot of atmosphere that blocks out the infrared. So we normally have to go to space for that. And then you go even longer, and there's the radio windows. And so there's a lot of ground-based astronomy. But if you want to go into high spectral resolution, these instruments are too heavy to put up in space. But from the ground, we can't see the atmosphere. So we can't see a lot of it because of the atmosphere. So it's a bit of a problem. So the solution is to put a telescope on an airplane to kind of bring the observatory up to the sky. And so this is what SOFIA was. It was a joint partnership between NASA and DLR, US and Germany partnership, where they took an old Boeing 747 and they cut a hole in it and installed a whole telescope into it. It was pretty ambitious, but it was really cool. And so this way it could, it kind of had the best of both worlds. So like space, you could get above most of the atmosphere, but like a ground-based telescope, when it landed, you could switch out the instruments, you could develop new instruments, fix old instruments. So there's the famous Hubble problem, where everyone probably knows Hubble needed fixing, so it's a big, daunting mission to fix it, whereas if you're on an airplane, you can fix it more easily. And so it's kind of like an in-between. And I got to fly on it twice, and it was really cool. Every seat was first class. But you had to bring your own food. They had like a little kitchenette, so you had to microwave your food yourself there. And it's also a bit different than a normal airplane because to keep the instrumentation very cold, they removed the insulation, so you really had to bundle up. We wore headsets to protect our ears and to talk to each other because it was really loud. And so each night was like a mission. Kind of very well choreographed.
So you were at some standard air pressure, right?
It felt like the air pressure felt normal. Like it flew higher than a commercial aircraft, but it was still, you didn't feel any altitude.
Was your cabin pressurized?
It was, so we were, except for being colder and louder, it felt like a normal airplane ride. Didn't feel any effects. So it normally flew at 40,000 feet, somewhere a bit higher, somewhere a bit lower. And the instrument team, they wanted always to fly higher. The pilots didn't necessarily want to fly higher. So they're always going back and forth about that. And the instrument that I did my research with was Ames, this spectrograph. And it was the only one that had high resolution that could access all of the mid-infrared. There's another sister spectrograph that's pretty much almost identical to it from the ground, but it can't access the whole mid-infrared. And these are, for year 2017, these were all its flights. It was based out of Palmdale, which is next to LA in the US. And then they also that year had a southern deployment out of New Zealand. These are very strange looking flight paths. And this is because, it had to end every night, of course, where it began, but also the selection of observations was a bit different than every observatory. So they would have the high priority ones, kind of guiding the science, but then they had to fill every observation with an opposite observation on the other side so that they could complete the full circle. And this is just
Because
visualizing.
the telescope doesn't point independently of the aircraft, or only within a narrow, does the telescope point independently, I guess is the question.
It only points out one side.
Yeah, there's only the hole in one side.
Yeah, but how much range of angle do you have?
I don't know. But yeah, it's only on the one side, so you had to.
You have to sort of.
Yeah, exactly. So you had to move the airplane. It had some type of isolating mechanism so that the motions of it were separate from the airplane motions. Yes.
These experiments are very similar to balloon experiments.
Yes.
Right? In that sense, I think this is significantly more expensive than a balloon experiment. But like, what's the real advantage of using a plane rather than a balloon?
Well, I'd say that, so I don't know too much about balloons, but it's much more reusable than a balloon. Because I guess I don't know for a typical balloon campaign how many nights you have, where Sophia, in theory, it just keep going and going and going and going and going every night.
All right. So in the long run, yeah.
But it was quite expensive, and that's why it got cut. It was a huge price tag in the budget. The research I was focusing on, that I'll tell you about first, is a survey of the Orion Hawk Core. And so this is an atypical source with an atypical target. But it's very well studied because it's in the closest massive star forming region to us. And about 500 years ago, there was an explosive event between some of the massive protostars in the region, known as EN and Source I, and pushed them apart, and they're still flying apart to this day. 500 years is very recent in astronomy terms, and I think it would have been really cool if we had developed technologies 500 years sooner. We could have watched this in real time. Unfortunately, we didn't. And this also causes these huge iron, ion, and H2 fingers reaching out from the region, the big picture, and the small picture is zooming in. The color map is from the mid-infrared, and the white contours are from the hot core. So this was actually the first hot core ever discovered, but it's an unusual hot core in that it's not surrounding a massive protostar, it's not internally heated. And the target we went for was IRC2, which is the second brightest source in the region. But this source is also not protostar. It's also externally heated, and there's different theories about its nature. Is it a cavity? Is it scattered light from source I? Other people say it's scattered light from another protostar, source N. So that I don't think what it is has been resolved, but it is a very bright mid-infrared source that's illuminating the hot core from behind. And so that's what we wanted to see is what kind of molecules can we see in the mid-infrared, because this has been surveyed a lot. This whole region has been surveyed along the radio, but not really the mid-infrared. And what did we see? We saw a lot of molecules, a lot of features. Most of them were absorption lines. We saw 2 species in emission. And yeah, we see this whole zoo of species, and some of these are not accessible at radio wavelengths because they don't have permanent dipole moments. And what we also found was that we found our velocity components did not line up with those found in the radio. And so just a bit in the weeds, just show how there's a lot of work involved with the spectroscopy. And so we have to take all these lines, all these hundreds of lines, and then we fit them to individual Gaussians. And why do we want to fit lines to Gaussians? Well, from this we can measure the depth and width of the lines. We can get an estimation of the column density of each individual line. And from there we use rotation diagram method, where essentially we're just plotting the energy of each transition versus the individual column densities, and we fit this, and out of this we can get the temperature and column density of the gas that we're looking at. And so we found double components, and these did not match up temperature-wise or column density-wise or velocity-wise with any of the established gas components in the region. So for the radio surveys that were done here, they have a giant radio beam and they point it towards the region, and then they separate into 4 kind of well-known, well-described regions. There's the hot core, and then there's also the quiet ambient gas they call the extended ridge. There's the plateau, and this is outflow from the ProStar candidate source I. And then there's also compact ridge, and this is where the outflow meets the quiescent gas in the region. And so our components were different. We named them the blue and red clumps because we weren't entirely sure what they are exactly, but they do exhibit chemistry related to the hot core. They have similar abundances, temperatures to the hot core, so we think it's gas associated with it somehow. Are we seeing a different portion of the hot core that the radio people saw? Are we seeing maybe something that came separated from it? We're not sure. Its interpretation is very difficult. And also because of the way the spectroscopy works is we have our beam over the source, but we're only getting the spectroscopy from the one target. So we don't know how far it goes. There is some complementary text observation towards 2 other sources, IRC4, IRC7, that show the same blue clump velocity component. So we know whatever we're looking at is probably covering further region, but we would need more research to know what exactly we're looking at in this region.
So some of your lines, most of your lines are absorption lines instead of emission lines.
Yes.
So what's the background continuum for those absorption lines?
It's IRC2 in our surveys. So it would be
You're
against.
pointing at IRC2, and if it's a bright source and not a void,
Yeah.
some of your models for it was that it was scattered light. So if it's scattered light, would that provide a background continuum for those infrared lines?
It would, yeah. And so looking into each different molecules, they can tell different stories, and we can get different information about the history of the gas we're looking at. So for acetylene, for example, it has 2 different states, as ortho and para state, where the spins on the hydrogen, if they're aligned or anti-aligned. And from looking at the ratio of these, we can see the ratio is closer to the ratio expected on formation on dust grains. So we can say that's the likely origin of the gas. And then also, along with HCN, we can look at the ratio of we got 2 different isotopes. And so this is a bit something that needs more resolution, is we found a low ratio of the 12 to 13C. And this is lower than expected for something of this distance from the galactic center. And also, when looked in the literature, other star-forming regions had the lower ratio. And so the question is why? We don't know why. There's a lot of things we don't know. We're just discovering stuff. And we don't have answers to everything. And another thing is looking at different species, looking at ratios of different species, we can tell formation history. So we see HCN and HNC, these are similar molecules, just with different order of atoms. And these ones are created at low temperatures with the similar abundances, but as gas heats up, their ratio changes. And so by getting this ratio and comparing to chemical modeling, we can age the gas, say it's been about 10 to 6 years since these molecules formed in colder conditions. Yes, of course.
About the H13CN,
Yes.
13 to 12 ratio. So you get a lower 12 to 13 than you expect. Is that expectation from like just gas phase abundances?
So it's been a while since I read the literature on this, but I know.
It seems like you're sort of looking at a region where you've heated up what might have been stuff that was on dust grains or depleted onto dust grains. So the dust grain depletion process can select out, a heavier molecule than the lighter one. So does that possibly change the expected, if the liberation of dust mantles is playing a role in which molecules you're seeing, does that change your expectations about the 12 to 13 C ratio?
Yeah, it could. So the papers were, actually that's a good point, because the papers where they measured it, they're looking at the relationship of the ratio with regards to distance from the galactic center, but I can't remember what they were measuring, like how they got that ratio. So it could be that, as you said, there's different processes that they're measuring for this measurement, whereas in star-forming regions, the molecules could come from a different process from dust grains.
Fancy name for that is fractionation or something like that.
Yeah. But that could be, yeah. And so there's one species, we call it a weed, SO2, because there's a lot of it. And so for this one, we use modeling to fit it, because there's too many lines to fit individually. So this is an alternative technique. And this was published in 2 papers, so I just want to also acknowledge all the work of the different people we worked with from different parts of the world, and also a lot of different expertise, because we had observers, we had theorists, we also had chemists, and this work brings in a lot of people together to help interpret the results and figure everything out. And so the second research program I'm going to talk about is Sophia Axe's Legacy program. So this was led by Ed Montiel, who was an instrument scientist at Sophia. And this was to create a library of bright mid-infrared sources. Unfortunately, not a lot of the program was carried out before Sophia's closeout, but we were able to get one very interesting source, NGC 7538 IRS1. So this is a massive protostar. I think it's about 40 solar masses. It's the brightest one in the region. It's surrounded by hot molecular core, and it's a very well-known, well-studied in the mid-infrared, and also at other wavelengths. So there's a huge literature just on this one protostar. And there's debate whether it's 1 protostar, 2, or 3. A lot of things are debated. And what we found was about 70 mystery lines towards it. And they didn't match anything in the known molecular databases. But we were eventually able to find that it's the torsional band of methanol, so that's when it's twisting, it creates these patterns. And it's a very interesting molecule because it's the simplest of the complex organic molecules. It's the basis for higher complex organic molecules. It's also a precursor to prebiotic molecules. And this is something that's very well known, that it forms on the icy dust phase, and then it's released at around 100 Kelvin, and the gas phase reactions are not efficient at forming it. So this is something that's definitely inherited from a previous state. And so we did the typical rotation diagram analysis to get out, okay, what's the temperature, what's the density of this gas, and we find that's comparable to previous radio surveys of it. And so you're missing out on a lot of gas when you just look at radio, not mid-infrared. And when we were doing the Gaussian fits, we did see two components. We also analyzed some acetylene. And so the Gaussians are not quite symmetric for a lot of them, but it wasn't resolved enough for us to actually quite measure the two components. But there were previous observations with taxis, that's the on ground-based spectrograph, where they had a bit higher spectral resolution, so they could see the two components. And so the question of always, what are we looking at? Where is it coming from? We have to indirectly infer what are we looking at. And so there's two possible interpretations. So the first thing is that it's debated where is the mid-infrared continuum coming from around massive protostars. Is it coming from the disk? So is the disk internally heated? Or is it that the protostar is heating the dust grains on the cavity walls and re-emitting, then these cavity walls are re-emitting in the mid-infrared? So which source kind of dominates when we're looking at it? And so if it is the continuum coming from the cavity walls, where are our absorption lines coming from? So it might be that we're getting the light coming from cavity walls, seeing it go through the outflow, and we're seeing absorption in the outflow. Or could we be seeing the mid-infrared light that's coming from inside the disk, and then the outer layer of the disk is absorbing the light, and that's what we're seeing. And we are favoring the interpretation of that the disk is heated, and that we're seeing the absorption in the outer portions of the disk. And so this because when we're looking at the two components, the velocities of them match with velocities found by other researchers around two protostars. So they're using, it was Maser research, and they kind of said, okay, there's two edge on disks, these are their velocities, and they're surrounded by a common envelope, and our velocities are very close to those. So we think we're seeing absorption towards the two protostars. And then similar work towards other massive protostars, and also using some more disk modeling. They also do feel that this is the interpretation of it. But I would say it's still a bit up in the air. It requires, I think, more work, more modeling, to really understand what we're seeing in the mid-infrared and which part of the protostar we're looking at. And so why do we care about methanol? So it's been observed in a lot of places. So with JWST, it's been observed in the ice phase towards molecular clouds. And with ALMA, we can see it towards the low mass protostars. We saw it towards a high mass protostar. And then also with ALMA, it's been seen towards proplanetary disks. And so it's being seen through all these different phases. And in particular, defining around proplanetary disks, this means that the methanol has been inherited from the ice phase because it couldn't possibly form the gas phase. And so this is kind of supporting a hypothesis that proplanetary disks will inherit their molecules. And then mid-infrared, we're opening up a way of seeing this molecule much closer into closer, hotter conditions towards the central protostar. There's other transitions in the mid-infrared, but we couldn't see them with Sophia X's or Texes because they're around 10 microns, which is in a very deep silicate feature. So the targets are very dim there, so we can't see that. And it's also on top of a molecular hydrogen line. So with a lower resolution with JWST, you won't be able to see that either. So pretty much this band we discovered for the first time is the only way to see it in the mid-infrared. And this was published recently in AppJ Letters, again with a lot of wonderful collaborators, with the chemists, the instrument scientists, and the legacy team. And so the future of mid-infrared, because there's no more SOFIA, is JWST, which is new and exciting and kind of breaking open, wide open, the mid-infrared. And there was complementary between SOFIA XEs and J2ST because SOFIA XEs was looking at super bright, the brightest, highest mass protostars. Whereas MIRI instrument, it saturates out for these ones, and so it's going to look at the low mass protostars, it looks at protoplanetary disks, and then it can also look at high mass protostars that are further away, like in the LMC or the SMC, that are dimmer. So it's more sensitive, but it has much lower spectral resolution. So it's much more difficult to, identify new molecules. In high resolution, their signatures are very distinct. In low resolution, everything gets squished together. So I thought I'd put some more pretty pictures of all the different things that MIRI-CAM can look at. Looking at nebula, where stars are born, planetary nebula, where stars are dying. Looking at a galaxy. Very nice. And so here's just one blown up image of all the different science you could also do with one spectra towards a low mass protostar. And in blue, there's the ices, the deep ice features, and these are the wide ones, silicates. These are some here. This is the deep feature it's talking about. And then the gas molecules are indicated in the red, so these are super small. And comparison between the low and high mass is only just starting. This comparison of the temperatures, I think I'm running out of time, but they pretty much, the low mass protostars are a bit on the low end of the range of the high mass protostars, but the comparison's only just beginning, so we'll see more stuff in the future. And yeah, so here I'm just illustrating really what we lost with SOFIA. So this is spectrum towards the same low mass protostar, and just zooming in on these water transitions, and then over similar wavelength with SOFIA towards a different target, there's all these different individual transitions. And so this is the real difference between the instruments. And I'd like to just finish off with what we're working on now at NASA Ames is the Space Mole database. And so I showed you those earlier slides where it's a lot of work to fit all those molecular lines, especially, I've got it pretty automated now. I'm used to doing it, but if you're just starting out, there's a huge learning curve for each observatory, each quarks, and each observatory's data, how do you even reading the data. And so what we're doing is we're going to do this for everybody so that we can put all those molecular transitions up. And these are observed molecular transitions towards targets, so it's different than the database that exists that show theory or lab work. So here you'll be able to search a target, any target, doing all of them, like solar system, planets, stars, protoplanetary galaxies, supernova remnants, protostars, everything you search. Put your target you're interested in, search the protostar, and then you can see what molecules have been observed towards it. So right now we're funded for doing SOFIA and Herschel work, so we're going to start there. And hopefully if that's a success in future, we can go to more observatories. And this is really to make this data, which has a high barrier to entry, accessible to anyone who's interested in it. And one used already, we're putting also the unknown lines up there. And we work with a lot of chemists, and chemists have no idea how to access astrophysical data, but they're always coming up with line lists of molecules they want to see, has it been seen anywhere? So now they can discover what these unknown molecules are. And we could probably find more cool molecules with this. And also for astronomers, when we find an unknown thing towards a target, the first question is always, what else has been seen towards this target type? And it's scattered across a lot of different papers, really big literature search, so everything's going to be here. So we're kind of excited what kind of new science we're going to enable with this. Yeah, I'd like to just finish with my conclusions, also my CITA mug, my really ancient CITA mug. So I actually got my start here as a student intern. This was my first summer project many years ago. I started astrophysics. and I still have the mug. It somehow survived all my moves. And yeah, I welcome lots of questions, lots of discussion. I'm happy to talk about everything. Thank you.
That's an antique mug. I had one, but it got stolen.
Oh.
So let's take questions online or room.
Yes,
Is Texas still going?
it is. Texas
Exes
is. So Texas is going. Exes is okay. I don't know what the research is. I don't know if, but Tommy Greathouse is the curator of Exes right now, and he's trying to find a home for it. Maybe on Gemini. So maybe Exes will have a home from the ground. I hope so. But Texas is going. I think they're always looking for more proposals to kind of create the pressure so that it gets used. Unfortunately, in US, we get grants for funding, so that observatory doesn't give us money. So, yeah.
So a lot of these complex molecules, at least the precursors to fancier things, are frozen out on the grains, and you show the ice and so on. But when you're in one of these hot core sources, they come off into the gas phase.
Yep.
But then that gas is also hotter, and so you get a lot of interesting chemistry, do you, that otherwise wouldn't occur in the interstellar medium, because you've got a rich soup of stuff to start with, and then it's hot, which is also important for
Yeah.
barriers. And is that well understood, well modeled, or is it just an at the idea level that yes, this is an important place for getting highly later generation molecules?
So I'd say there is a lot of modeling, especially zero-dimensional modeling with it. So they can model everything up, but I would say my own perspective is that what it means, what all these molecules mean, is still not certain. So we can observe them, we can find them happening, but what does it mean physically? So it's talking about inheritance, but can we actually model that? Can we see where the molecules that end up on Earth come from, at what stages? That would be something to take this.
Yeah, I guess that's an interesting question. You get these fancy molecules, but then what's the delivery success to planets like ours?
Yeah, how do they survive? And then also in the interpretation, we need more modeling, just seeing where in the layers, okay, the disk versus the envelope, where the whole story, the whole picture of just what are we looking at with the spectroscopy, I think needs a lot more modeling for the interpretation of it. Because I think we need to know where they are before then we can say what they mean.
Sarah, very nice. I'm just curious, like, are these metals properly mixed in these protostars, or do they, like, what's the chemical mixing like? Is it homogeneous?
So we can't really see stuff in the protostars themselves.
Sure. Yeah, but even in the disk,
In
for
the disk
example,
envelope.
is it really homogeneous, or is it chemically inhomogeneous? Like, what does it actually look like?
That's a good question. So I think to answer it, one would have to look at the observation of different wavelengths. So compare what we're seeing mid-infrared versus the millimeter versus millimeter to see if they have different compositions. I don't think anyone's ever done that. because then you could trace the profiles in the different regions. See if the closer regions have a different mix of molecules than the further out regions. Yeah, that would be interesting.
Maybe we can chat more later, yes.
I can't see, can you see online? I'm not
Oh, yeah.
open it, whether it's, well, I guess people could just speak up.
Does anyone online have any questions?
Just read.
Yeah.
Okay. Well, for now, if there's no more questions in the room, let's do our usual, go upstairs and have more discussion over refreshments, and let's thank Sarah very much. Well, you can just unplug her and then
It is recording, so we should stop. Probably leave. Hang on one second, it said stop that, I guess. I can't do that, so I think we'll just leave that, turn off.
there we go.